The objective of Lab 3 is to find the mass of a black hole by using a computer model. The computer model takes the position data of a star which is orbiting a black hole and finds the star's velocity and momentum and the net force acting on the star, and then it uses that net force and Newton's universal law of gravitation to find the mass of the black hole, which in this case is 2.388 times 10 to the 31st kilograms. I calculate the net force by using the derivative of the star's velocity with respect to time. I can calculate the momentum because velocity equals delta x over delta t and p equals mv. To calculate the derivative, I use the approximation delta p over delta t, which is valid when delta t is small. I also calculate the parallel and perpendicular components of the net force so that I can draw arrows representing them in the model. I can use this net force in Newton's universal law of gravitation, which states that the force of gravity is equal to the universal gravitational constant times the mass of the star times the mass of the black hole, all over the distance between them squared. We either know or can calculate everything except the mass of the black hole, which we can rearrange the equation to solve. This is the form of the equation that I use in my model. I start off my model by identifying my known values. I then iterate over the position data and find the velocity at each point by calculating the change in position from the current point to the next point and then dividing that change by the time step, and then I append that velocity to an appropriate list. I then iterate over those lists, and at each point I calculate the momentum and the change in momentum and then use that to calculate the net force. I then calculate the components of the net force and update the graphics and calculate the mass. When I run the program, you see the star orbiting the black hole and you see arrows representing the net force acting on the star. You also see that the average of the mass calculations is 2.388 times 10 to the 31st kilograms. I say average because there is some variation in the calculated mass, which you can see from this graph that I made by writing the calculated mass into a CSV file. This is due to several factors, including noise in the data, which just means that the data isn't as good as we thought it was, rounding error due to scientific notation, because we truncate the last part of the number, or other approximation error. One of which is that the velocity, which I'm treating as the instantaneous velocity, is actually the average velocity over a small time span. Nonetheless, the difference between the largest and smallest points is only 0.00013 times 10 to the 31st kilograms, which is only 0.01% of the average mass. One important thing to remember when doing this lab is the difference between dp dt, Fnet, and delta p over delta t. Recall that Fnet is equal in magnitude to dp dt and that delta p over delta t approximates dp dt. Now realize that dp dt is the change in momentum, but Fnet causes the change, and cause is not the same thing as effect. Also, approximate means close but not exactly to, so dp dt is not exactly the same as delta p over delta t. Another thing to realize are the limitations of this program. If the substitution described above were to happen, I would not be able to find a different mass from the one I calculated before. This is because the star's motion depends only on the star's mass, initial position and velocity, the black hole's mass, and the net force on the star. If nothing but the mass of the black hole changes, that means that the black hole's mass also remains constant. The average of my mass calculations is 2.388 times 10 to the 31st kilograms. Each individual result is consistent with the other results to within 0.01%. The model allows me to do these calculations quickly and consistently, which I would not be able to do anywhere nearly as well if I did it by hand.